Grundmann. He brought his own laptop, so we're gonna set that up quickly. University Leipzig, professor at the University of Leipzig, and also the CEO of Saxon-Q. Saxon-Q has patented NV technology using diamond-based qubits, effectively combining energy, efficiency, and scalability. And it looks like everything's working just fine. That's a clicker.
Yeah.
Dr. Grundmann, stage is yours.
Thank you very much. Welcome to our presentation. The Saxon-Q stand is over there, and you can see our quantum computer in live operation, which is maybe the most interesting part. So, das funktioniert aber noch nicht. Now we go. I think I have to stand here. Jetzt will nichts mehr machen. Here we go. Okay. So our quantum computer works with the so-called NV technology. I will explain what this is. And that means that we have solid-state qubits for calculating. It's a scalable technology. The qubits are high fidelity. And we are a full-stack company, so we develop the hardware and the software to execute the agnostic code on the computer. So just to tell you about the technology a little bit, everybody knows what diamond is. So in the diamond, if you think about a millimeter-sized ring, maybe a little bit more for your wife or so. A factor of 100, you come to a blood platelet. Another factor of 100, you come to the current gate size. And another factor of 100, you go to the nanometer range, and we look at single spins in the solid. So the solid-state qubits are single atoms in the computer. And this is the computer, how it stands over there. It has currently 4 qubits. End of the year, we have 8 qubits, and then goes in powers of 10. And it's very small. It can be plugged into the normal socket, and it works at room temperature. Now, in order to explain what a qubit is worth, let's look at popular computers. When I grew up, when I started to study, the Apple I was a popular computer. Nowadays, we have this MacBook Pro or whatever kind of computer. And the key features are an increase in memory size, of course, also an increase in computing speed. And the first computers had 64 kilobytes, 160 kilobytes. And this computer has gigabytes or terabytes. If you calculate that memory into qubits, it goes logarithmic. And such an Apple I computer has about 20 qubits. And during 45 years of PC development, the number of qubits that is equivalent to the memory has doubled. So doubling of qubits means an extreme progress in the capability of a quantum computer. So the quantum computing, as most of you probably know, is based on 2 effects, quantum mechanical effects. One is superposition. In the previous talk, we talked about interference, so this is kind of a little bit of a superposition, if you want. And the second effect is entanglement. We also heard about entanglement. It's when 2 qubits or several qubits are entangled. You do one operation to one qubit, automatically the other qubits react to that. So they get connected, and that's very important for the quantum computing. Applications will be everywhere. It's acceleration of solving complex mathematical problems, for example, in optimization, machine learning, cryptography, and so on. Now, our machine is very small. Why are other quantum computers so big? Because they need the cooling, they need a lot of infrastructure, they need vacuum, cooling, a huge media, liquid nitrogen, liquid helium, and so on. Our computer just needs a socket. It is mobile, it is portable, and the next generation will be already smaller than what you see at the stand. Please go to our stand. Our staff will explain it to you and demonstrate it live. So, why does it work at room temperature? Well, the diamond crystal is hot, 300 Kelvin room temperature. But the qubits are decoupled from the lattice, so they are actually very cold. While this computer operates, the qubits are close to absolute zero, but the crystal that hosts them is warm. So there's some interesting physics behind that. We use a little bit of carbon, which is a diamond chip. We use a little bit of gold, which is the wiring. And we use just a few nitrogen atoms to make this chip. So the NV center, the NV technology means we implant nitrogen with a patented process. And in the diamond lattice here, we replace one carbon atom with a nitrogen. And next to it is a V, a vacancy, a Leerstelle. Yeah? So we have this system which provides us an electron spin. These qubits have a long coherence time. We couple the electron, which is here the NV center itself, with nuclear spin qubits. So we have the nitrogen and other carbon-13 nuclei, Atomkerne, and those have an extreme long coherence time because nuclei, as we know from MRI imaging or so, are decoupled largely from the environment. So one NV center gives us between 4 and 10 qubits, and we'll see about the scalability in a second. The point about quantum computing is that you do not look while you operate. The measurement, of course, destroys the quantum state. So you look at the final result only, and while the quantum computation goes on, the system should be decoupled from the environment, which is exactly the case for this. But in the end, there's a spin-photon interface. We measure the spin state via optical means. There's also another possibility implemented soon, reading it out electrically. So we have a good interface to read out the quantum information. But while we are not reading out, the system is doing its quantum mechanical thing. Also in the system, but that's maybe more for the experts, we can easily facilitate multi-qubit operations. Normally, what is done in computers, you only couple 2 qubits. So you have 2 qubit gates. But in this computer, you can have 3 qubit gates, 4 qubit gates, and so on, which facilitates operation. Also an important point is the topology, how the quantum qubits connected. Here in this case, the connectivity of a transmons and the superconducting computers. If you have n qubits, you have about n connections. In our system, you have about 2n, so it's a little better, or a factor of 2 better than the transmons. It's a scalable technology. We use one NV center for 4 to 10 qubits, and then we make more qubits. So here, for example, is a row of 4 NV centers. So 4 NV centers give you 16 to 40 qubits. So 40 qubits is almost the memory that is in this computer. Yeah, the entire memory of this computer can be imaged into 40 qubits. Here's an example. I have to speed up maybe a little bit. Here's an example, for example, using 2 NV centers. So you see here 2 peaks. You can switch them. It's like a swap operation. And using 2 NV centers, we're going to go to 8 or 20 qubits soon. The interesting thing is about how is information transferred from one NV center to the next. Well, here's an experiment I show as a professor at the University of Leipzig. It is 2 magnets that can swing. I don't have a video right now for you, but you see in the time traces how they swing. So 2 magnets can interfere, interact, have a oscillation. So this is the same thing, just about 1 billion times larger than our NV center. So it's a kind of a model experiment. And as we know, this so-called dipole-dipole coupling goes with the 6th power of the distance. So the qubits need to be close to each other, but this is exactly what we actually can do. Now let's talk about the scaling again. It's important that we get to more qubits, but it's also important that the system size doesn't increase exponentially with the compute power. The effort that we need to do in terms of resources, material, electronics, energy that goes into computer cannot grow with the compute power, but it needs to grow maybe only linearly with the number of qubits, or maybe even sublinearly with the number of qubits. So if we think about the transmons, each qubit needs 4 or 5 wires. So if you talk about 1,000 qubits, you need 4,000 or 5,000 wires that go into that cryostat, which is not really a scalable system. Our qubits arranged in an array need, for 1,000 qubits, only 30 or so lines. So it's very easy to control, and you do not need so many control lines to run the system. So here's the chip. If you have a few more lines, here's a 3x3 array. So of course you need to address those with individual lines. But if you have a higher scale chip, it will look like this. And such a chip is very close to making like 1,000 qubits or so. And that's an important point. Quantum computing needs to be sustainable. It needs to lower the CO2 footprint of what we try to calculate. We will have compute power in a machine of this size that is nowadays in a Großrechenzentrum, in like a high-performance computing center. And in order to that, we need to lower the energy budget. And the energy budget of this computer, of our computer, is really low. It's much less than 1 kilowatt. It's in a stationary operation about 600 watt. So we need to lower, as a long-term perspective generally, the energy we need for performing complex calculations. Also, it's a very small, robust, compact system that generally just doesn't need a lot of things in order to perform the quantum calculation itself. So it's really a low energy budget, sustainable system. Also, since it's solid state, it is virtually maintenance free. It will work until whatever breaks first. Stuff always breaks at some point, after 100 years at least, but it will operate for years without maintenance. We have the computer very soon in the cloud. You can see also the cloud interface, so you can download your code. Currently, the computer understands OpenQASM and Qiskit, so you can execute your Qiskit code on the computer. You give it via the cloud web interface, and then you can design either your own quantum gates, or you choose predefined use case algorithms that we have predefined, or you just write your own Qiskit or OpenQASM code, and this will be then executed on the computer, and the result will be given back in the queue and the cloud mechanism. So Section Q has a solid state technology, and the unique value proposal is you have a machine that you put up in your own company, in your own site where you need the quantum computing. It's a proprietary technology that uses semiconductor planar manufacturing. So it's a semiconductor type of technology. There are high technical merits. We have high fidelity qubits, time stable qubits, and the operation is at room temperature or at any temperature. You can also cool it if you want. It's robust, it's small, has a low energy budget, and it's suitable for mobile installations because it's fairly small. And it can be locally installed at the customer, so you have 100% control over what code is executed, what algorithms you execute. Nobody else will know because it's just with you. And you can also use 100% of the QPU time. So it's just there for you without any latency. So here's our team. A couple of very skilled team members are at the stand. They're happy to demonstrate the machine directly to you. And yeah, we're happy to answer any questions, and we're happy if you order a machine. Thank you for your attention.
Thank you very much. And let's see if we have some questions in the room.
I'm happy if you have a question to answer.
And otherwise, where is Sachsen-Q?
Sachsen-Q is located in Leipzig.
Yes,
in general. And it's just when you come in there, close to the exit there.
Okay, perfect.
On the left side
so the team is there.
Yeah, team is there.
But let's see, maybe we have one or the other question left. Yeah, there is one. From Diatopy.
Oh, here we go.
Thanks, Marius, for the nice introduction into the company and what you're doing. Can you maybe address the main technological problems which you face currently, set them in perspective with the current state of number of qubits, and tell us a little bit about how you're going to solve the problems? Thanks a lot.
Well, the main point of the technology is to create the qubits, which is a process we already have demonstrated. So, as I said, a factor of 2 in qubits is not a trivial thing. You have to work and develop a little bit for it. But currently we're working on 2 NV centers, so this will give you 8 qubits or more at low temperature, up to 20 qubits or so. And then you go from 2 to 4 NV centers. That's the idea. And that's the implementation process. And yeah, it needs to be precise enough, but that's fine. No problem.
One follow-up we have. One follow-up question, please.
You said that you're gonna put the NVs, and they're gonna give you one NV gonna give you some number of qubits by coupling to C13 nuclear spins. How long do you have to look for an NV until finding one which shows the necessary coupling, and how much control do you have over the number of qubits of the NV?
Well, we have an implantation process that has a very high yield. So if we implant NV pairs, for example, the yield is, well, nothing has 100% yield, but most of the NV centers turn out to be really pairs. So we don't have to look forever. Like in the previous literature, it was a random act, and the poor PhD students had to look a long time to find the one center for which they can publish a paper. But now it's a standard process to make coupled NV centers, and it's a high-yield process.
Okay, thanks a lot.
You're welcome.
Thank you for the question.
Thank you.
So is there anything else that you would like to address? I think we're fine.
Okay, yeah, thank you very much.
Thank you so much. Thank you so much for the presentation. Thanks for being with us.
Dann ziehe ich das hier raus. Gut.